Hello everyone, let us continue our discussion. We are in week 11 and this is our first lecture. In this series, we are going to learn strain energy and its applications. So we'll first define what we mean by strain energy, and then we will see how we can use this strain energy to solve the structural engineering problem. Now, before we discuss with an example, as you can see, we have a bar and this bar is experiencing a force P. Obviously, it will undergo some extension, say L, and L is the length and A is the cross-sectional area. And as we consider only linear system, so our entire discussion is for linear structure only. Now for this case, if I draw the load deformation behavior, P versus delta for this bar, so the bar will experience some kind of extension and this is the delta. So we can plot the P versus delta, which starts from 0, and because we have a linear structure within elastic limit, then if we load the structure, it will follow this path. If we unload, it will again come back to its original position. So for zero loading, it will regain its original length, right? Now, for this example, if we find out what is the stress applied, it is the P load acting over a cross section. So we can define the stress. We can also define strain, which is sigma divided by Young's modulus. And in place of sigma, we can write P. So it is P divided by AE. Now, strain energy stored due to this elastic deformation within this body is the area under this curve. So strain energy normally represented by capital U. Recall we earlier used small u for deformed shape. So now we use capital U for strain energy. It is the work done by the external force, that is P, and which is half times P times delta. Now we can quantify delta. It is nothing but the strain times the initial length, right? And in place of strain, we can write P by AE. So we have PL by AE as the total elongation. So this quantity is then P square capital L divided by twice AE. So this is the strain energy stored within the body due to this elastic deformation. Now, the same expression we can actually derive. For that, let us consider a differential element. So this is a length dx at a distance x. Now, the strain energy stored, say, du over this small segment here is half times sigma times epsilon times dV. So now we can further modify it. So we have epsilon as sigma divided by E. So we have sigma square divided by E, and dV we can write cross-sectional area A times dx. Now in place of sigma we can write P by A. So we have half P square by A square times E, and then we have another A here times dx. So we can cancel this A here, and now we have the expression. So du is this quantity. Now if we integrate both sides, then the left hand side will get the total strain energy stored within the body, and in the right hand side we have P square, then L divided by 2IC. So we can see that the same expression we have derived, which we had earlier here, right? And what is the definition of strain energy then? When a body deforms elastically due to the action of some external force, it develops some strain and it also stores some energy within the body because of this deformation, and that energy is called the strain energy. We also sometimes define strain energy density, which is small u. Strain energy density is total strain energy, which is capital U, divided by the volume. Now again, I draw your attention that small u is the strain energy density here and not the displacement that we solved in the previous week, and also this V is the volume and not the shear force that we earlier studied, right? So we can define the total strain energy, and sometimes we also define strain energy density. Just like material density is the amount of material per unit volume, it is the strain energy per unit volume is defined as the strain energy density. So this is the strain energy when a bar deforms under the action of a load P. Now let us slightly modify this problem. So we consider the same bar, but this time instead of some external load, it deforms under its self weight. Let us see how much is the strain energy that we have in case of a bar that deforms under its self weight. So we again consider a differential element of size dx at a distance x. Now for this problem, P, that is the load acting, is the weight of this segment. So we have x times A is the total volume times the material density is rho times G is the total force acting on the body. So we can calculate sigma. Sigma is equal to P by A, and that is equal to rho G times x. Now, what is the volume of this small area marked here? It is the cross-sectional area times dx, right? So the strain energy is equal to half sigma times epsilon times dV. So what we can do in place of sigma, now we can write rho G x, and in place of epsilon we can write sigma by E, so it will be the square divided by E, and in place of dV we can write A times dx. So what we have here is rho square G square times A times x square dx divided by 2IC. So that is the strain energy stored within this element. So if we integrate both sides, we get total strain energy within the body. So that we can easily work out. So we have rho square g square a by twice e as constant. So we can take it out of this integral. So we have 0 to L x square dx. So effectively we have rho square g square a L cube divided by 6e. Now if we multiply numerator and denominator with a, we have a square in the numerator, and you can see rho g times a times L is the total weight. So square of that, so we'll have W square times L divided by 6AE. So that is the expression of total strain energy stored within this body when it deforms under the action of its self weight. Right. Okay. So now we have learned how to calculate strain energy for a bar which is under uniaxial extension only. So let us extend our problem, and now let us consider bending of a beam. So we will get bending strain energy, right? As you can see, we have a simply supported beam, and then we apply a moment at the end of magnitude, say m. As you can see, this is a sagging moment, and the deformed shape of the beam is what you can see on your screen. Obviously, it will have a radius of curvature. We have already studied in detail the bending of a beam, and this is the radius of curvature, and the angle theta is here. Obviously, the more moment we apply, this theta will be more, and the beam has length L and flexural rigidity EI. Now for this beam, strain energy U is equal to the work done is half times moment that we apply times the deformation we have theta. Again, it follows the same logic. If we plot m theta, that is the load deformation curve, so it will start from 0, and as we increase moment, it will linearly vary. And again, I repeat, we are dealing with linear structure only for the time being in this course, right? Now, again, the area under this curve is the total strain energy under bending. So this is the strain energy. Now recall, during our discussion on bending of beams, we defined kappa, which is d theta dx, and for this beam we have constant moment applied over the entire length. For this beam we have then theta divided by L, right? So we define radius of curvature, and from there we can also get curvature, right? Okay, so now capital M is equal to kappa times E times I. So what we have, theta times EI divided by L. This we have derived earlier. So we get the expression of theta. Theta is equal to ML divided by EI. So if we put that expression here, we have half m square L divided by EI. Now for any beam having any arbitrary loading, if we consider a section at a distance x and consider a segment of size dx, then we can again find out the strain energy stored over this element, and that is, as per definition, half mx is the strain energy stored times d theta is the strain energy stored within this small element, right? So we consider this small element. Now recall d theta dx is equal to d2u dx2 is equal to minus m by ei. In fact, this is the equation we used in the previous week to solve the deformed profile of a beam under any loading. Okay, so this is the moment acting at a distance x, and for that moment we have a deformed profile which is defined by u. Again, I draw your attention, this is capital U, which represents strain energy. Sometimes strain energy density we represent it using small u, but in the previous week we used this small u for the displacement field. Okay, now we have d theta is equal to mx dx divided by ei. Now this negative sign comes from the sign convention that we have used. If we use a different sign convention, obviously that will be different, right? Okay, so the magnitude of the rotation is d theta, and that you can see here. So if you use that expression here, we have half then mx square dx divided by ei. So that is our du. So if we integrate both sides, and then what we'll get, the left hand side we have the total strain energy, and right hand side we have 0 to L mx square dx divided by twice ei. Now it is same when we have constant moment over the entire length. So we can integrate this expression. Mx is m, what we have here, and then dx integrated over 0 to L will get L. So we'll get the same expression what we have here. Now we have the expression for bending strain energy. This expression is generic for any mx at a distance x from the left end is here, and it can be used to find out the total bending strain energy of a beam that is undergoing some bending deformation. Okay, so we'll use this expression actually when we solve some problem in a minute, but before we solve some problem, let us first define all the strain energy and then we'll take the problem. Now the next case is the shear deformation. So in case of shear deformation, we'll have shear strain energy. For that, let us consider a small section, small area of size delta x and delta y. And then obviously under the action of shear deformation, it undergoes, so this shear deformation, so that is delta of gum. So the net shear deformation here is delta x times delta. Okay. So the strain energy stored because of this deformation is half the shear force acting over this section times the shear deformation, which is delta x times delta. Now recall from Hooke's law, we have delta gamma is equal to delta tau, which is shear force for area, divided by G. So that expression we can use here. What we get is half v square delta x divided by Ag. So total strain energy is half v square times the dimension divided by A times. Now normally this is very small. Compared to bending or torsional strain energy. So in normal problem we neglect this. However, we have the expression. If we wish to calculate the strain energy due to shear deformation, we can calculate that using this expression. Now let us define the last one, that is torsional strain energy, before we take some examples. So torsional strain energy. As you can see, we have a shaft whose inner radius, this is R1, and then outer radius is R2, and then we apply a torque here, say T. Obviously, this end also we apply the same T. Now for this problem, let us first define strain energy density. So strain energy density is small u. Again, it is not the displacement strain energy density here. So it is half times tau times gamma. So we know tau is equal to G times gamma, and this is equal to torque T times R divided by IP. If you recall, we derived this expression in the previous weeks, right? So what we have here is half tau, and in place of gamma, we can write tau by G. So we have tau square. So we have half T square R square divided by G times IP square. And then we have the strain energy density. We can also find out the total strain energy. And let us do it from a different analogy. So what we consider is a small annular ring, as you can see, at a distance of say rho, and this is a small annular ring. So what is area? Area is 2 pi rho times ds. So the strain energy stored is D of capital U is equal to strain energy density times we have dA times L. Now we can put this expression here. So what we have is half then T square rho square, because R here will be replaced by rho, divided by G times IP square times we have L times. So to get the total strain energy, we can integrate both sides, and this will be from R1 to. So what we have here on the left hand side, we have capital U, that is the total strain energy, is equal to T square, then divided by twice GIP square, and we have R1 to R2 rho square dA, and times we have a L here. Now this quantity is the polar moment of inertia IP. So effectively we have T square L divided by twice G IP. So that is the expression of torsional strain energy stored within the shaft. Right. So now we have the expressions for axial strain energy, bending strain energy, shear strain energy, and torsional strain energy. So we have all the expressions. Now we can take some problem, right? So our first problem is a cantilever beam. So this is example 1. So in this problem we have a cantilever beam subjected to a point load at the free end. So this is P, and the length of the beam and EI is given. Our task is to find out the deflection of the beam at B. So let us mark the ends. So we have A and B, and if we can draw the deflected pattern, we have, this is the deflected pattern, and this deformation is delta B. Our task is to find out the deformation at the free end using the concept of strain energy, right? So for that, what we do, we consider a section at a distance x from the point load P. We can actually start from the other side, from the support, but then we have to find out the reaction, the force and the moment at the support, and then we have to consider both of them, but it is easier for a cantilevered beam to start from the right end. So we have mx is equal to P times x. Now the bending strain energy, we have already derived the expression. So bending strain energy is UB, which is equal to 0 to L m x square dx divided by twice EI. So this is equal to 0 to L. In place of mx, we can write px whole square dx divided by twice EI. So if we solve this, we get p square divided by twice EI, and 0 to L x square dx, that will give us L cube by 3. So the total bending strain energy we have UB is equal to P square L cube divided by 6 EI. Now, what is the work done by this force P at the free end? So the work done is half times P times the deformation there, that is delta B. Now, if we equate this to, because of this action of this external force, we have the bending strain energy stored within the beam. So we have W is equal to UB, and then what we get is half times P times delta B is equal to P square L cube divided by 6u. So now we can solve delta B, which is P L cube divided by 3. Right. So you see how we can use the bending strain energy to solve the problem, right? Let us take a different problem. Our example 2 is a simply supported beam and the beam is having a UDL of omega. So the intensity of the UDL is omega and the length of the beam and EI of the beam is given. So our task is to find the bending strain energy stored within the beam. For that again, let us solve the beam first. So we have the ends A and B and the reactions at the end is omega L by 2, omega L by 2. Next what we do, we consider a section at a distance x and we find out what is mx. Mx is equal to omega L by 2 times x minus omega square by 2. Now we can find out bending strain energy UB is equal to 0 to L mx square dx divided by twice EI, which is equal to 0 to L. In place of mx, we can now write this expression, which is actually, if I take omega by 2 common, we have Lx minus square. So we have here omega by 2 times Lx minus x square, square of this quantity times dx divided by twice EI. So we can evaluate this expression. So what we have is omega square divided by 8 EI, which is constant, and let us take it out of the integral. So we have 0 to L, then L square x square minus twice L x cube plus x to the power 4 times dx. And if we complete this integral, we have L square x to the power 3 divided by 3 minus twice L x to the power 4 divided by 4 plus x to the power 5 divided by 0 to L. So effectively we have omega square L to the power 5 divided by 8 EI, and within bracket we have 1/3 minus half plus 1 by 5. Now if you simplify this expression, you will get omega square L to the power 5 divided by 240 EI. So we have evaluated the bending strain energy stored within the beam due to a UDL of intensity omega is omega square L to the power 5 divided by 240 EI. That solves the problem. So now you can see how we can use the moment at a section X, and for this moment there will be some deformation, and because of that elastic deformation we'll have strain energy stored within the body, and that we can quantify as you can see on your screen. So let us stop here, go through these derivations, and we'll continue on this topic in our next lecture. So we'll use this bending strain energy and we'll see how useful it is and how to solve the deflection and slope over the length of the beam. That we'll study in our next lecture. If you have any difficulty, do let us know through email or in our open session, and we will definitely clear your doubts. Thank you very much.